Very good morning, one and all. I am Kavitha, Assistant Professor, Department of Civil Engineering, VSB Engineering College. Today we will discuss about the tension and compression members. Some introduction part we will see today. So these are all the main contents. This is the course objective of this unit, and also the textbooks and reference books for the same unit. So first of all, we would like to introduce the design of compression members. So first of all, what is mean by compression members? The structural members, it is subjected to the axial compression. Mainly it is axial compression load, compressive load. It is subjected to the members. So this is called as a compression members. So mainly it will cover the strength and buckling area. It have two types of compression members all available. So especially in steel structure, the columns and structure also as a compression members. So the sections are used for the compression members are, in theory, the numerous shapes can be used for the columns to resist the given load. But in practical point of view, the number of possible solutions is severely limited by the selection of availability and the connection problem and other types of the structures. So in which the section is to be used. So these are all the main types of sections, compression members using in a practical solutions. So this is a single angle, double angle, T, channel and W columns and pipe sections, and also the square HS rubbing sections, right? So and also we have some rectangular section, box sections also. So these are all the main common sections are available. So in this column member, we have some effective length criteria, how it can be varied. So up to which category it can be varied. The column connections in the end condition is very important here. So what are all the end conditions we are going to provide here? So both end of the column can be hinged, the both end of the column can be, it may be fixed condition. The combination of hinged and fixed, it is one end is fixed, another one end is hinged. Maybe the one end is fixed if the another one end is free. So these are all the end conditions of the column. So based on this end conditions, the effective length can be varied. So we can see one by one. So this is the column conditions. The both end conditions are pinned connections. For that the L effective value can be varied. So likewise we have another one condition. One end is fixed, another one is free. One end is restrained, another one is free. So both ends are hinged, both ends are fixed. So likewise each and every conditions the effective length can be varied. So L is equal to 2L, L is equal to 0.5L, L is equal to 0.7, as well as our K value also varied. So if it is fixed, one end is free, one end is fixed means K value is equal to 2. So both end conditions are fixed means the effective length of the L is equal to 0.5L. The both ends are fixed. The K value also it may be a 0.5. So likewise the pin and fixed ends, that means one end is fixed, another one end is fixed. So for that condition the L effective value is 0.7. For L is equal to 0.7, L is equal to L effective. So for that the K value also varied here, it is 0.7, right? So these are all the effective length criteria based on the in conditions. So what does mean by slenderness ratio? We all know it is the effective length of the column divided by minimum radius of gyration, right? So this is the ஒரு common example of the slenderness ratio. So what does mean by the radius of gyration? It may be I by A, right? We all know, right? In a moment of inertia by the area it is called a minimum radius of gyrations here. So what is the lambda? It is L effective divided by R. This is the formula here. Why are speaking the slenderness ratio here? If the slenderness ratio, that is lambda, if more, what will happen? It's a load carrying capacity will be less. So thus that is the main uh, parameter here to consider as a compression member column strut members. So if the lambda is more, what will happen? The load carrying capacity will be less. So that is the reason we are providing here as a slenderness ratio. Next one, how the compression members are failure. We have three criteria here. What are all these three criteria? So there are three basic types of column failures are available. Usually we can classify the columns short, long and medium column, right? So first of all we have to discuss with the compressive material failure. What does mean by the compressive material failure? It is a crushing failure, that is called. It will happen only in very short columns. If it is buckling failure, when it will be happen, the column is very long. So at that situation, this buckling failure will be happen. Why the combination of the both compressive and buckling failure, where it will be happen? So both combined, or the combination of compressive and buckling failure, it will happen in both column is between the strut and fat and long columns. The combination of this short and the medium column will get the compressive and buckling failure. So this will happen, right? So these are all the common failures. Next one is local buckling. How it will be local buckling? So this is the one example of local failure. So what will happen? It is only happened in the thin section, not fully buckling. The modes of failure can occur before the mode of failure can occur. It will happen. It's buckle only locally in the compression member. So that is called local. This occurs when some part or parts of X section of column are so thin and they buckle locally in the compression before the mode of buckling can occur. So next is flexural buckling. What means flexural buckling? So it's also called as Euler buckling. So this a primary type of buckling members are subjected to the both bending and the flexural force. So that will become, it will be become an unstable condition. So what will be happen? So after automatically the flexural buckling will be happened, right? So next one is some compression members are squeezing. So it will be some prevention of the local buckling. Then the column will be able to attain its full strength before failure, like our ultimate yield strength, right? So the column, when the length of the column is relatively small, what will happen? And the column is chalky and its components plates are prevent from the local buckling, then the column will be able to attain the full strength before it's failed. So that is called squeezing. So next we'll move to the tension member. So it is some introduction part about the compression member. Now we are going to the tension members. I will explain some introduction part about the tension members, right? So what is mean by tension members? So the tension members are linearly structural member. It is subject to the axial forces. It will along to the member. It will be yield. Some examples of the tension member is wired ropes of a cables, stayed bridges supporting by decks, or the bottom cord. This may be a bottom cord, right? This bottom cord of a stress member, and also as the member is subjected to the pulling forces. If there are pulling forces is acting, means that will be a tension forces. Pulling force as it elongate and does not buckle before, no need of classifying the type of sections. So these are all the simple definition and the examples of the tension members. So these are all the types of cross sections of the tension member. So these are all the types of cross sections we already know, right? So the tension members may consist of single rolled sections and combination of this build-up section also. Usually, so in this section, the single and double angle sections with gusset plates and commonly used for truss members. If we are using the truss, if considering the truss member, that truss member we will use the gusset plates arrangements with single and double angle sections, right? And also rods and flat plates may be used for bracing system in the truss and the build-up column. While using the build-up column section, we have to provide some bracing arrangements. So for that bracing arrangement, we will provide some flat plates. So that will be another one cross section, right? Then next one is the wire rope sections and cable sections of in where it will be using in the suspension bridges. So these are all the different types of the cross section in the tension members. So these are all the slenderness ratio for the tension members. So this value we can take it as from the IS 800 2007. Directly we can take this value in from the code book, right? So these are all some another procedures of the design of tension members. This also derived from IS 800 only. So we have some criteria here. What are all the criteria? If the design strength, that is TD of the member, shall be greater than the factor tensile force. The strength should be greater than the force. That is DT is equal to TU. So in this DT may be at least of these three values. What are these three values? Design strength due to yielding, design strength due to rupture, design strength due to block shear. So we have to each and every design separately to do the design procedure for separately. We will do this yielding process and rupture and block shear. We have some criteria here. First one we will discuss. So this TD value, the strength may be at least of these three values. So we can see one by one, right? So this is the design strength due to yield of cross section. So here we will consider AG as a cross section of the total gross area of the cross section. We know what is by lambda, it is a partial safety factor. We can derive from IS 800. Fy means yield strength of the material, like 250 MPa, right? So this it can be derived from each and everything. Finally we can calculate it DCT, that is the design strength due to the yielding of the cross section. Next one, the design strength due to rupture of a critical section. How it can be calculated? The same, dn is equal to 0.9 an divided by fu into gamma l, right? So this fu is can be calculated by the ultimate tensile strength of the material. Likewise we can also get this from. So here we have to consider one more factor. What is the one more factor here? Means if the bolt sections are arranged in a straight line manner as staggered manner, that is zigzag positions. If they are arranging zigzag positions, mean we have to calculate this type of values. If they are in a chain bolting, like as a straight line bolting, we can use this an formula, that is d minus n into dh into thickness. If they are arranging staggered positions, we can get this value to calculate the design strength of the rupture, right? So another one is a single angle. So in this design we have another one, thread and single angle. We have a two formula for calculating each and every one. And also the reduction factor also here, this is beta as a reduction factor, we have to include this in this category. It is a single angle section. Final one is design strength due to the buckle shear, block shear, like a block shear DTB. So this also can be derived from IS 800, right? So we have another one formula here. So this failure of the end section is a unit along the center of the bolt, right? The holes in the tension and the shear plane is termed as called block shear, block failure. So this block shear of strength is at least of this two. So we can take this formula and this formula. So DTB1 is another one formula and DTB is 2 or another formula. So this will be using for calculating block shear. Why we are calculating this shear, rupture and yielding? So we can take it as a strength from these three values, least of these three values compared with the force. So next is the same thing, it is here, it is mainly for shear and the tension, right? So this is the introduction part about the tension and the compression member. This is the course outcome for this unit, and thank you.